So yeah, thank you for the nice introduction, and thank you for the opportunity to be here. Yeah, I'm Jonas. Most of you know me already. I've been here for 3 weeks. I will stay 1 more week. And I'm doing my research in Germany, in Karlsruhe, at the robotics lab of Tamim Asfour. And today I'm going to talk about safety aspects when learning robot trajectories. This was the topic of my PhD thesis, which I finished recently. And I'm also, towards the end of the talk, going to talk about my future research directions. So since you're all experts in robotics, I'm going to keep the introduction short. As you know, industrial robots are very fast and they're also very precise, and that makes them perfect for industrial production plants like the one you can see here from Tesla in California. But all this only works in case that the environment is completely known in advance and all the movements can be hard-coded in advance. And in case the environment would change, this would no longer work. And if we compare this to humans, we have a completely different approach towards learning robot movements. Humans are much more flexible. They can adapt to different tasks and different environments. And this is also because we can learn movements by trial and error. And the technical equivalent to learning by trial and error is reinforcement learning. And here you can see how the number of publications on reinforcement learning has developed over the last few years. And since the year 2016, of course, due to the success of neural networks and deep learning techniques, the number has increased significantly. So I know you are familiar with reinforcement learning, so that's why I just want to give a short. So in reinforcement learning, we have a state space S, we have an action space A, and we have a reward function that assigns a reward to every action taken in a certain state. And our objective is to find a policy that optimizes the sum of expected rewards in the future. So what I did in my PhD, I worked on the topic of generating robot trajectories in real time, considering safety constraints. And in my case, each state considered information about the robot, the environment, and the desired task. Then the state was given into a neural network. The neural network output an action, and this action is used to compute a trajectory from the current time step t to the next time step t+1. And after the execution of this time step, a reward is calculated, and this is used to train the neural network.
How long is the time step typically?
In my case, between 50 milliseconds and 100 milliseconds. So I usually use a frequency of 20 Hertz or 10 Hertz. Depends a bit on the task.
So it's a trajectory, that means you have many points in between, t+1? Or?
It is like I compute the trajectory, yes, for 100 milliseconds, but I interpolate the points that are in between that are given to a joint trajectory controller. And this frequency is, of course, higher. So this is usually 200 Hertz for the robots, for these industrial robots I work with. These are from KUKA. Yes. And the actual research question was, how can we make sure that these actions are mapped to trajectories that are safely executable? And in this talk, I'm going to talk about 3 techniques that are used in my PhD. The first one is an action mapping, which ensures that kinematic joint constraints are satisfied when generating trajectories. The second technique uses background simulations of braking trajectories to additionally ensure that also collisions with static obstacles and self-collisions can be avoided. And in the third part, I will talk about a way to extend this technique so that also moving obstacles can be considered. And this is done based on a data-based risk estimation and learned backup behaviors. So for the sake of time, I'm only shortly talking about the state of the art, but in general, there are 3 directions to approach safety in reinforcement learning. The first one is a practical perspective, and this includes strategies to reduce the occurrence of safety violations or to reduce their impact, mostly based on engineering, like the design of the environment. For instance, if we have a bipedal robot, we could use a support frame and attach it to the support frame so that the robot cannot fall even if it loses balance. And there's also the more theoretical perspective on the problem. What we can do is we can adjust the optimization objective. So this function that tries to optimize the sum of future rewards, we can, for instance, include an additional risk metric to this function to avoid safety violations during the course of training. The problem with these approaches is typically that they are not very effective at the beginning of the training process, because the optimizer needs to collect data in the environment first before it can optimize this objective function. And the third approach, and this is also the approach I used in my PhD, is to adjust actions that are considered risky and to replace them with actions that are considered safe. Okay, now I'm going to talk about the first part, this action mapping, considering kinematic joint constraints. So what does this mean? If we have a robot joint, revolute joint or prismatic joint, we can describe the position, in this case of this revolute joint, based on an angle. And when we generate our action with a neural network, we more or less need to define the curves of this angle over time, so from t to t plus 1. And when we do this, we need to make sure that certain constraints are respected, in particular constraints on the position. The first derivative of the position is the velocity, the second derivative, that's the acceleration, and also the third derivative, which is called jerk. And if we do this, we will end up with smooth movements that do not overload the robot joints. So what is usually done, what's the state of the art? Often in reinforcement learning, actions are mapped to constant velocities. So for instance, if you have a normalized action of 0.6, it is mapped to a velocity of 60% of the maximum joint velocity, and so on. And if we do this, we get continuous positions by integration, which is nice. However, the position limits can also get violated depending on the selected actions. And as we can see, the velocities are discontinuous, and that means our acceleration limits are violated, and also, of course, the jerk limits are violated as well. And now the question is, can we ensure that every action leads to a trajectory that respects these kinematic joint constraints? And the answer is this is indeed possible. And what I did during my in my PhD is I computed a so-called upper trajectory and a lower trajectory, and the action was used to specify an intermediate trajectory between these two. And the upper trajectory is a time optimal trajectory to the maximum joint position. You can see this here. And that should reach the maximum joint position at a velocity and acceleration of 0. And the lower trajectory goes to the minimum position, also at an acceleration and velocity of 0. And now when we, these trajectories can compute it analytically, the time optimal trajectories. And now if we have a closer look at the relevant time interval from t to t plus 1, we can just say, in case our action is -1, our resulting trajectory can follow the lower trajectory. If our action is 1, it can follow the upper trajectory. And for intermediate values between -1 and 1, so these actions refer to every joint. For each joint, one action between -1 and 1 is generated by the neural network. We can select an intermediate trajectory. And the nice part is when we do this and we generate completely random actions, as it is the case at the beginning of the training phase, you can see that the trajectory is able to go close to the limits, or like the robot can work at the joint limits, but still it never violates the limits, no matter which actions are selected here. And this is nice because then we can learn very fast movements without destroying the robot joints from a kinematic perspective. And I use this action mapping for different tasks, for instance, to track reference paths specified in joint space while considering additional objectives, in this case, a so-called ball and plate task. This means the robot should follow a path that was specified in the state while balancing a ball on a plate. And yeah, I use this action mapping and the default structure for reinforcement learning. The reward was calculated based on 3 components. The first one rewarded the length of the generated path to make sure that some progress is made along this path. The second component punished the deviation to the reference path, and also this ball balancing objective was added so that the ball stays close to the center of the plate. And yeah, I used PPO to train the neural network. And here you can see some results. So on the left side, the robot is trained without this additional ball balancing objective. In this case, of course, the ball balancing doesn't work. And on the right side, the ball balancing is also rewarded so that the robot can learn to keep the ball close to the center of the plate. And I also use this to adjust reference trajectories. So in case of a reference trajectory, it is shown here without any adaptations. The timing of the trajectory is already given, and the neural network tries to generate a trajectory with the same timing, but that can balance the ball. And yeah, here you can see some results in simulation. So the networks are always trained in simulation, but then yeah, they can be transferred to some degree to a real robot. In simulation, this worked in 89% of all cases. And for the sim to real transfer, the balancing still worked in 82% of the cases. Yeah, so this action mapping is quite nice because the kinematic constraints are satisfied, but it's still not perfect because when we start our training process and let's say we have a robot mounted on a table, we will of course have collisions with the table due to the random movements executed at the beginning of the training process, or if we use like a humanoid robot with 2 arms, the arms will also collide. So in this case, these are self-collisions. So in the second part of my talk, I would like to talk about a technique to avoid also these kind of collisions during the training process. So just a short recap, we are at time step T. We know our action AT task generated by the neural network. We can map it to a trajectory from T to T+1. But what we do not know is the future trajectory starting from T+1 because it depends on unknown future states. And what we now additionally want to do is we want to avoid collisions. So now the idea is maybe we can perform a safety check by simulating the next time step and the future trajectory in a physics simulator. However, as we do not know the future trajectory, this doesn't work directly. But it turns out it is sufficient to know one way to continue the trajectory that is safe, a so-called backup trajectory. And in case that we have a robot with a stable base, so typically industrial robots have a stable base, this humanoid robot also has a stable base. Of course, robots with legs do not have a stable base. In this case, this wouldn't work. But in these cases, we can use a braking trajectory as a backup trajectory. And a braking trajectory is, as the name says, a trajectory that leads all robot joints, the velocity and acceleration of all robot joints to 0. And the benefit of using such a braking trajectory is that once the robot is stopped, no more collisions can occur. That means we only need to simulate the future trajectory until the robot is stopped, so until the end of this braking trajectory. And this means we usually have a short time horizon that we need to look ahead, which is good when it comes to the computational effort for the background simulation. So I want to give you a short example how this works. So let's say we are in time step t and we select an action, and then this action specifies a movement from t to t plus 1, and then we add our backup trajectory and we perform a simulation, a background simulation in the simulator, and check if collisions occur during the simulation. So let's say no collisions occurred during this background simulation, then we know we can execute our action AT task. And this is shown at time step t plus 1. So by executing this action AT, we end up in time step t plus 1. And now we repeat this procedure and we get another action AT plus 1 task. But also before we execute this action, we once again perform our background simulation. And now it turns out we detect a collision during this background simulation between the hands. And what we can do now is, instead of executing this action that we got from our neural network, we can instead execute an action that is slowing down the robot joints. And this action will lead to exactly this situation that we simulated at the time step before. And this is, and due to this, we know that following a braking trajectory from this state, there will be no collision. So it's safe to execute this action at this point. And yeah, here you can see a comparison where I trained this robot to reach the target points on the left side without action adjustments. And in this case, collisions occurred in 65% of all episodes. And on the right side with this technique, where actions are replaced. And in this case, no more collisions occurred during the training phase, and of course also at the end of the training phase. But even with this technique, there are still some limitations, and one limitation is moving obstacles, because the assumption was that once the robot is stopped, no more collisions can occur, and this is not true if we have moving obstacles in our environment. And I tested this with different environments with moving obstacles. And in order to extend the technique also to environments with moving obstacles, we can now say, okay, instead of using a simple braking trajectory, we can use an optimized trajectory that tries to avoid safety violations. So this braking trajectory is replaced by a backup trajectory that avoids collisions, and this is done based on an additional second neural network, also trained with reinforcement learning, that tries to avoid collisions with moving obstacles and also self-collisions and collisions with static obstacles. But if we do this, two additional problems will arise. The first one is the time horizon that needs to considered when executing this trajectory in a physics simulator in the background, because now that we have moving obstacles, we need a longer time horizon that needs to be taken into account. And that means the computational effort for these background simulations will be relatively high, and it is hard to execute this in real time. And the second problem that occurs is that we also need to know the future movement of the moving obstacles. And this is also not easy, since we in general cannot completely forecast the movement of moving obstacles. And to address these problems, the third technique that I want to talk about introduces a data-based risk estimation. That means we initialize the robot in a lot of random states. We select a lot of random actions, and then we can, in a physics simulator, execute this trajectory from the next time step plus the backup trajectory. And we can check what is the outcome, is there a collision or is there no collision, and collect data points by assigning a risk signal to each data point. So if there's no collision, we say our risk is 0. If there is a collision, we say our risk is 1. And then we can specify data points with the state, action, and this risk signal. And all this data can then be used to train an additional neural network, so-called risk network, to estimate the probability of a safety violation when executing our action AT task in our current state. And then we can say, okay, if our probability or our expected probability is higher than the so-called risk threshold, we won't execute the action from the neural network, but the action from the backup network. Yeah, here you can see some results that I achieved with this approach. So the base of the robot indicates what is done. So green means the task policy is executed. Red means the backup policy is executed. And based on this risk threshold, we can then adjust how risk averse our policy will behave, even in environments with moving obstacles. And this can be used from the beginning of the training process, this approach. And since this risk estimation with the risk network is really fast, we can also execute this in real time. Yeah, so this was more or less what I did during my PhD. So just to sum up, the first part was this action mapping so that kinematic joint constraints are considered. Then I added a technique based on background simulations to ensure that also collisions are avoided in the static obstacles and self-collisions. And this technique was extended using a data-based risk estimation and a learned backup policy so that also moving obstacles can be considered. And yeah, so now I just want to talk in the last part of my talk about some challenges that I identified, some ways to improve the techniques, and also a bit about what I'm trying to work on in the future. So one challenge, of course, that I didn't address is the inclusion of visual feedback. So when I trained the neural networks, I usually used low-dimensional input spaces. And so, yeah, low-dimensional states, more or less kinematic state information. Yeah, and of course, visual feedback would be great also when it comes to considering different tasks, so multitask learning. In this case, we could add, for instance, an embedding considering demonstrations or textual description to our state so that we could learn a policy that not only is able to perform one task, but also different tasks. However, a big challenge when we want to do this is also the definition of the suitable reward function. So what I found in my work is that it is really not so easy to find a good reward function for a task, and that is why a lot of researchers use tasks where it is easy to define a reward function, but then if you want to apply it to a real-world application, things are pretty difficult because you need to find a working reward function first. So for instance, when it comes to multitask learning, there is a benchmark. It's called RBench. It's a benchmark with 100 robot tasks, which is really nice to evaluate your techniques on different robot tasks. But also in this case, the problem is only 3 of these environments provide a shaped reward function. And that is why most people use this benchmark with demonstrations and use imitation learning or behavior cloning to get a policy that is able to work in different environments. And now one idea could be to say, okay, instead of defining explicit reward functions, maybe we can use some kind of a database estimator for rewards, and ideally based on videos or a textual task description, So the research question in this case is, can we, for instance, use a multimodal large language model as a reward estimator? And that is what I'm currently looking into. So in fact, we have 3 different options to use the knowledge of a multimodal LLM for reward estimation. Option 1 would be just rely on the data and the knowledge the network already has. Option B would be in-context few-shot learning. That means we give some examples to the neural network, to the LLM, and hope that it is able to estimate rewards based on these, based on a small number of examples. And the last one would be fine-tuning in case that we have access to the network parameters. And yeah, how to do this exactly is still a question of ongoing research. One example would, one way could be to give the network a small video, a task demonstration, and also an input text, what the robot should do, and then give an image of the current time step and the next time step, and a potential reward signal, and hope that by giving a few examples, the network can understand what the desired objective of the task is. Another potential way would be to give also an input video and an input text, but in this case, ask the network just which of a couple of potential different outputs are better, so that we could do some kind of a ranking. And this could be used for so-called direct preference learning to optimize the neural network parameters. So that's ongoing research, and that's what I'm currently looking into. I'm also not 100% sure which option will be the best for this. But yeah, so that is basically what I wanted to show you. Thank you for your kind attention. And yeah, I'm happy to answer questions.
Can you explain again about the action space?
Mm-hmm. So the action space I used regarding the kinematic joint constraints.
Right,
yeah. Yeah, of course.
Action mapping.
Yeah, maybe I go a bit. Oh, yeah. Yeah. So yeah, what I did is at each time step, I compute these time optimal trajectories. So a time optimal trajectory to the maximum position and one to the minimum position.
From current position to maximum. And
yes.
Time optimal solution.
Yes, and a time optimal trajectory to this target state, and this is possible with existing motion libraries because yeah, this problem can be solved analytically. So there are motion libraries where you can specify a kinematic target state and compute a time optimal trajectory just considering these constraints. And now
the idea of time period from T to T, you also specify?
I mean, this will always go like to the point where the maximum is reached. So this is just an example. In this case, it takes like 15 time steps, but all this is actually not so important because what I only need is like the next, the first time step. So this visualization is more or less to show you what the upper trajectory and lower trajectory would do if we would execute them. We only do this in case that the action is always 1. So assume like the action would be 1 at each time step, then we would follow this upper trajectory and then the robot would stop at the maximum position at a velocity and acceleration of 0. And likewise, if we select -1, we would end up at the minimum position. But in practice, this case rarely occurs because usually the action is something in between, like this case, and then we end up in a new kinematic state. But since this trajectory is always in between, it cannot violate the limits. You know, it can never be like outside of our velocity limits if this upper or lower trajectory is not outside of the limits, because it will be in between. And of course, we also need to ensure that once we are here and we compute a new upper and lower trajectory, that the solution will exist. But this is indeed the case, because if we would assume that the same distance between the upper and lower trajectory is also kept for all following time steps, not only for the next time steps, but for all time steps until this time step, then we would also generate a feasible trajectory. And that means if we take only one step, we can be sure that at least one feasible trajectory exists. And this could be used as a fallback, but this usually doesn't need to be used, because since one trajectory exists, we will always find a new upper and lower trajectory at the next time step. And that is what is shown on this image. So here you can see at each time step, like the upper and lower trajectory is recomputed. And at some time steps, we have the situation that these also fall together. So in this case, no matter which action would be selected, the robot will always execute the same movement, because otherwise, in this case, we would violate our velocity limits.
You are always choosing in between this maximum and low.
Yes.
Your action will be closing, right? Within this limit.
So the trajectory will always stay in between. So it could be or like exactly follow the lower or upper trajectory case of the corner cases, -1 and 1.
Could you explain about
Yeah. Okay. Yeah, sure. Of course. Yeah, so the idea with the braking trajectories is that, let's say we execute our action in order to make sure that we are still in a safe state after executing our action. We need to know that there's at least one trajectory that we can follow that is collision-free. And what is done here is we check before we execute our action if the robot can be stopped safely after executing this action. And if this is the case, we know we can execute this action, because if we do not find a safe action in the following state, we can always safely slow down the robot and end up in a state that is considered safe. And so the braking trajectory just slows down the robot joints, but I guess the relevant slide is maybe this one. So we always compute our braking trajectory. We check, this is like, let's say this is one time step, this is the next time step, and this is one more time step. And here at this situation, the robot is at a standstill. Then we can simulate all this, and we can check, is this trajectory collision free? And if that's the case, we can safely go from this time step to this time step, because we know we could execute a braking trajectory without ending up in an unsafe state. And in case now in our next time step, this doesn't work, so for the next action, we do not find a safe braking trajectory, and that means this state is considered as unsafe. But from this state here, we can always go to this one by executing an action that brakes the robot, that slows down the robot, and this state we know it is safe. So let's say in case we wouldn't find a safe action from this state, we could always go to this state from which we know that it is safe. And from now on, from this state, since the robot is at a standstill, the state will always stay safe. So that is the basic idea. And in case that we have like the situation where we do not have moving obstacles and the robot can be stopped at each potential position. This of course doesn't work if you have like a robot with a floating base or with legs. Then the robot might simply fall if you stop it at a position that is not stable. But in case the position is stable, this always works, and yeah, make sure that you do not collide. Sure.
I have a question. So this process is during training?
Yeah, during training, but usually also during evaluation. So it's more or less always used. You could also use it just for inference. So say you train it without this, and then you use it only if you execute like movements with the real robot. But typically, then your task performance will go down when you execute it only during inference and not during training. It's also, to be honest, like if you do this, in this case, for instance, like here the robot is trained without this technique. On the right side, it is trained with this technique, and around 10% of all actions are adjusted. And due to this action adjustment, the task performance will also go down a bit. So in this case, it was around 2.3 target points per second that the robot reached. And on the right side, it was 2.1 target points per second. So there's a slight decrease in performance when you do these things like adjusting actions, because this, if you adjust like 10% of the actions, these actions won't contribute to the actual objective of the task. So you also need to make sure that this adjustment rate isn't too high. So let's say you need to adjust 50% of your actions, your task performance will probably not be too good. But if it's like 10%, it's okay. So the impact will be moderate. Yes.
Have you considered solving this problem through constraint auto formulation?
Constraint reinforcement. Constraint reinforcement learning. So I mean, there are different approaches to address these kind of problems. So as I said, during the state of the art, for instance, it is also possible to use constraint learning techniques. There are some special algorithms which can handle safety constraints during learning. This would be like go back. So what you probably refer to are techniques that try to use methods from constraint optimization to optimize like this objective function subject to additional constraints. This is possible to some degree, of course. The drawback from my perspective is that these techniques do not really work well at the beginning of the training process. And also I found in the literature there are different kinds of constraints. Some are called instantaneous constraints that need to be satisfied at each time step. This is like the kind of constraints I looked into, and there are also so-called cumulative constraints. So these refer to a sum of a penalty that needs to be restricted. For instance, if you have like a car and you have a limited amount of fuel and you say we have a safety constraint that the fuel doesn't run out. And in particular for these kind of constraints, there are some algorithms that work very, very well from constraint optimization. But yeah, I mean, there are different approaches to address these kind of problems, and I guess every algorithm, every way has benefits and has also some drawbacks. And also the literature there are really a lot of different safety constraints. So it's really hard to say we have one algorithm or one technique that can handle all kind of problems. And yeah, what I focused on in my work were techniques for this specific problem of learning movements with these industrial manipulators, and also trying to make sure that these techniques can also work at the beginning of the training process. But of course, yeah, there are also a lot of different other approaches that also might work well in a lot of cases.
A question for the risk estimation network.
Mhm.
For the dynamic obstacle, is the position of the obstacle is included in the state? Or
The current position of the obstacle is included in the state, yeah. But the following, so let's say this can in general be measured. So if you have like an obstacle and you can probably detect the current position. Of course, in the simulator where I use this, I always had access to the perfect position and so on. And of course, if you use it in a real world environment, you would have a sensor and you might have some sensor noise or maybe some latencies and so on. And all this might decrease your performance. But in my case, I had access to this, to the position of the obstacles. But what I didn't need due to this risk network is knowledge about the future movement of the obstacles. And this is in contrast to when you try to perform these background simulations with the simulator. Then you need to assume that you know how the obstacle will move in the future. And in this case, due to this data-based approach, the network will try to learn the risk depending on the future movement of the obstacles. And this can also be stochastic to some degree. So for instance, like I had this human environment and the human moved a bit stochastically, so you could not really say how it is moving, but you could say, okay, it will probably not move in a completely odd way. Then you can still try to estimate risks for such a situation.
did you train separate risk estimation network on the real robot, or did you use the same network from the simulation?
Yeah, so in this case, I used the same network as from the simulation. I mean, it would also be possible to train a separate one. But of course, this training also of the backup policy and also of the risk network, it naturally involves that you have risky situations. You know, you need like some data points where you can say, okay, this would end up in a collision. And this, of course, is a bit difficult if you want to execute it on a real robot, because then you somehow need to make sure that even if you have a collision, the robot won't be damaged. I guess it would also be possible to some degree to do it on a real robot if you have like a protected environment, or let's say you define safety distances or something to make sure that you can do this. But for this work, I collected data in the simulator.
Do you think that risk reduction can be integrated with the policy network somehow, like estimating action with the risk?
So as one kind of a network.
Yeah, like one single network
One.
to estimate the action and risk of it.
I mean, in theory, this could also be possible. The benefit a bit of the approach I showed is, so what I do, I train a backup policy first, then I use this to collect data, then I train the risk network, and then I train the task policy. And the benefit of this way of doing it is that you can train separate task policies using the same backup policy and same risk network. So because in this case, our risk estimation doesn't depend on the task policy. There are also alternative approaches that do it a bit differently. So instead of predicting the risk and following this backup policy, you could also predict the risk of following the current policy that you learned. But so this is an alternative approach, and when you do this, you can derive a backup policy based on your risk estimation. But if you do this, the drawback is you always need to update these networks during your training, because then your risk network and your backup policy depend on the current policy. And this will also be a bit problematic at the beginning of the training process. But in general, this is an alternative approach that could also be used to address these kind of problems.
좀 많이 한 것 같습니다.
So yeah, thank you very much again. Thank you.